Okay. It is Monday, April 19th, and we are in the process of studying hypothesis tests, right? Honestly, I'm a little concerned. We only have 8 of you, actually 9 if I count better. So we've got less than half of the folks here. But hopefully the rest will watch on video. All right. I don't know whether I had mentioned when we're going to have the test on hypothesis testing. My belief is I would like to do that a week from today. Okay. So a week from today will be a test on everything hypothesis testing. It will be similar to the last test. Talking about the last test, I have not completed grading them, but I have started the process and looked through them. Once again, it seems to me that the easiest questions are the ones that you had the most difficulty with, which were the ones at the end of the test. Okay, the multiple, wasn't multiple choice because you got to put down any answers you wanted, right? So if I look at that, number 6, that a manufacturer of outdoor furniture is trying to understand the improvement and strength of the steel used. If it is testing to see how much more weight the chair will hold before breaking when they used hardened steel versus regular, it is assumed that the standard deviation of the two samples are identical. Which statements are true? Mark all that apply. A is absolutely true. We will need to collect 2 sets of samples. You're going to have to take one set of samples from the chairs that were made with the regular steel, and you will need to take another set of samples from the one that uses the hardened steel. So you can test both of them. Second one is the 90% confidence interval will be wider than the 95% confidence interval. No, to be more sure, what? The more sure you want to be, the more padding you have to put on both sides. The more padding you put on both sides, the wider it gets. So the 95% confidence interval is going to be wider than the 90th. The 99% confidence interval is going to be even wider, right? 80% confidence interval, we get smaller and smaller as we go. So B is not true. C, to do this problem, the population standard deviation needs to be known. You can't do this problem using sample standard deviation estimates. That's not true. There was that whole section in the formula that I said we were not going to do because it was relatively complicated in terms of the math, okay, or at least more complicated than it was worth. But you can do it, and that's what that formula is. It calculates the pooled standard deviation, right? The D, the pooled estimate of sigma, will give you a better estimate than sampling sigma from each one, and that is also true. Okay, and I do not know why it's claiming that my cord is not working. All right, it's giving me the warning signs that, all right, unplug and replug, and the computer is happy. All right. Sorry about that. Number 7, you find the 99% confidence interval for the percentage of fish with ick disease in Lake Placid is 4% to 7%. So you are 99% sure that the percentage of fish with this disease is between 4 and 7%. You're 99% sure it is between those two numbers. Well, the game warden says it's 3%. Okay, mark all that apply. Is it possible that the game warden is right? Well, you're 99% sure it's between 4 and 7, and he says it's less than that. He says it's 3. Is it possible he might be right? The answer is, yeah, it's possible. Is it likely? No. Why? Because you're 99% sure it's between 4 and 7, right? So you only have a 1% chance that it is either higher or lower than that number, right? So then B, the probability that the game warden is correct cannot be more than 1%. That is true. Okay? You're 99% sure that it is that range is entirely outside of where he claimed, and there's only 1% possibility of being in the tail, which is what the tail game warden wanted. Since the game warden is the professional in things related to fishing, he must be correct. No, that's why you take samples every now and then. Since the game warden is a government employee, she must be wrong. You might think a lot of government employees, but that's not it. Okay. Anyways, those were, I think, the simplest, well, in some case, simplest of questions if you had followed along. Anyways, the other ones, for the most part, I would say the people who did well did very well, and the people who didn't do well, just you have the best way to phrase it is, I think you have reading word problems, doing word problems, and you're not finding the right things to take out of the problem, and you're not filling in the blanks. So you're not filling in the appropriate things for what is n, what is x bar, and so on and so forth. And there are two possibilities for that. One, which I would be extremely, I guess there's three possibilities. One is that you just have no freaking idea what I've been talking about. Okay? You don't know what a sample size is. You don't know what a sample mean is, and all that type of stuff. So that since you don't know what the letters mean, you can't find the right answer. Okay? That is one possible reason why people have done poorly on that. It's the one I hope is least likely to be true. Okay? The second one is that you have reading, that somehow when you read word problems, your brain goes to mush. Okay? And I think that one is the one that is more likely the case. And in that case, you know, although I don't want someone to, you know, you to be working with someone, okay? My guess is that had somebody explained that situation to you, right, and you went off and did it, you would have gotten it right. Okay? But there's something about reading that all of a sudden says, oh, here's a number, I've got to plug it in somewhere. Instead of reading the problem, figuring out what is the final result going to be, and then asking yourselves the question, okay, just as a reminder, right? How big was my sample? That's N, right? Let me go reread that paragraph. How many people were interviewed? How big is the sample? You know, where's the N? X bar was what? The average from the sample. Well, let's go back and reread that and find that, right? So my sense is that had someone not given it to you in written form, but talked to you about it, or talked to you while you were on the dock of the bay, you'd be able to figure it out. It's just somehow the reading issue is a problem. The last possibility is it's a possibility of, you know, that some of you have some degree of dyslexia. Okay. I think I have some of that, that you just write the wrong things in the wrong spot, and your brain doesn't even recognize it's in the wrong spot. Okay. Anyways, so those are that type of issues. But some of you probably have known that for for most of your life, you had problems doing word problems. Okay. All right. Again, hopefully, you know, I had hoped to have those graded by today. I fell down on that job, but hopefully we will have those done in, you know, hopefully tomorrow. Okay. All right. We are now in hypothesis testing, right? And in hypothesis testing, there is this methodology that is if you use, be reasonable, do it my way. Don't try to learn this out of the book, learn it from me, all right? And this is one of the reasons I'm really a little bit worried that there were only 10 of, well, grown to 10 of you. Okay, that's a little bit better than 8. But that's still less than half the class, right? And how do we do these hypothesis tests? Okay, and I will use the step process that I did before, and let me just see if I can pull that up really quickly. Okay, it's not on my recent list. I've got to pull it from the internet. Okay. All right, this content on our home page. I am going to our Blackboard. Okay, if you go down, there is a folder off the main page that says how to do hypothesis questions. Okay, and this is a quick PowerPoint that consists of 3 pages. All right, go back to here, do a screen save, not a screen save. Okay, where am I? I have to share my screen. Bear with me while I talk to myself. Share application screen. Okay, you guys should see the title, How to Do Hypothesis Testing Problems, an 11-Step Method. Can somebody just verbally say, yes, Professor, we see that?
Yes, sir, we see it.
Super, thank you. All right. The first step, steps 1 through 6, the first step is make sure that the problem is a hypothesis test question, right? Okay, Read the problem. If it's asking for a confidence interval, it's not a hypothesis test question, right? If it says something else and you are not testing or trying to prove your particular point, okay, it's not a hypothesis test question. The second step, once you've determined that it's a hypothesis test, you've got to determine what is the null hypothesis and what is the alternative hypothesis. The general rule of thumb is the null hypothesis is what you will continue to believe if there is not compelling evidence that it's wrong. Okay? So as we are speaking right now, the defense attorneys in Minnesota are doing their final, in the court trial of the police officer, are doing their final jury presentation, right? The prosecution's H0, well, what is the null hypothesis in a criminal trial system? It is that you're innocent until proven guilty, right? Okay. If someone has not actively proved their case, we will continue to believe that the null hypothesis is true. The alternative hypothesis is that the null hypothesis is not true. So in this world, the null hypothesis is he is innocent. The alternative is he is not innocent and hence found guilty. The alternative hypothesis is what the prosecution has to show. They are the ones that have to prove beyond a reasonable doubt that H0, the null hypothesis, is exceptionally, beyond a reasonable doubt, not feasible. That the probability of all of the evidence could have happened purely by chance if the person was innocent, practically never, beyond a reasonable doubt. Okay? They are trying to destroy the null hypothesis. The defense attorney does not have to prove the person is innocent. He just has to stop the prosecution from proving it didn't happen that way, that he's not innocent, right? He just needs to put a doubt into the equation so that there is a reasonable doubt whether it's H0 or HA, at which point the judge will instruct people that the null hypothesis that he's innocent should be continued if the prosecution has not proven that that is exceptionally unlikely to be true, right? In business scenarios, we're usually looking at numbers, not court cases, okay? And so what we end up dealing with is one-tailed or two-tailed tests, right? That was step 3. Is a null hypothesis claiming something is equal, which in case you could be wrong on the upside and you could be wrong on the downside, which is two-tailed. Or is there only one direction that the null hypothesis could be wrong? Okay. Question number 4 is sigma known? Or do we have to use S, the sample standard deviation, in its place, right? The 5th question is, are we going to be using a Z table or a T table? which comes from number 4. If sigma is known, it's going to be Z. If sigma is not known, it's Z if you've got a large N, or T if it's not. And then we have in number 6, what is alpha? What level are you willing to tolerate making a type 1 error? A type 1 error means that the null hypothesis was actually true, and you call the person who said that a liar. So in the case of the criminal case that's going on in Minnesota, the null hypothesis is that he's innocent, that the officer did not kill your fellow Javelina student, right? And that he died of other causes, right? Or didn't die at all. I don't know what the alternative is, right? But the null hypothesis is that the police officer is innocent. If the police officer truly was innocent, what is the probability that the jury gets it wrong? That probability of getting it wrong in that direction, finding an innocent person guilty, is a type 1 error. Alpha talks about your willingness to tolerate making that type of a mistake. Okay? Everyone, when they do hypothesis testing, will eventually make a mistake. If alpha is 1%, you are to 99% of the time, when the null hypothesis is true, you will not reject it. Okay? 1% of the time, 1 out of 100, when you have alpha equals 1%, okay, you're willing to accept that you made a mistake. If you wanted alpha to be 0, then life is really simple. How do you make sure you don't ever convict an innocent man? Just plain say, regardless of what the evidence is, I don't care. I don't care. He's innocent. He's innocent. He's innocent. Right? If you never say he's guilty, regardless of what the evidence was, you will never convict an innocent man. Now, you're going to let a lot of guilty people, alternative hypothesis is he's not innocent. You're going to let a lot of those people off the hook. But that's not a type 1 error. We will call that a type 2 error. Alpha talks about the probability that you will be making a type 1 error that you are okay with. Then step 7 through 11 is here. And this is where we start with drawing our charts. The top chart is our X bar. It's what we got from the sample. And underneath that in the blue is what we get from the standard normal. And then we have those dotted lines that kind of go between the two. Once we have drawn that, okay, we then have to find either the Z or the T cutoff values, depending on, what was it, step 4, whether we have a Z or a T, right? And we will get that from understanding what percentage are in, what percentage of the tail is in the tail. If we have a 99% in the middle, that means we have an alpha equals 1. That means the total shaded area is 1%. If we have a two-tailed test, which is the example on the left-hand side, right? We split it into two different sides of the normal curve, at which point alpha divided by 2, half of it is going to be in each tail. If we have a one-tailed test, then the entire alpha is in one tail, and you have to figure out which tail the rejection region is and which one is the acceptance region. Right? Once you have done all of these 9, now in step 10, 9 and 10, we go and actually get the average from our test. And we can calculate the test statistic. And then we compare that test statistic number to the blue chart. And we look on the blue chart whether that test statistic is in one of the shaded rejection regions in the blue region. If yes, we reject the null hypothesis and accept the alternative. If it is in the unshaded area, we accept the null hypothesis. So we do this process every single time. If you draw it this way and you go through these 11 steps methodically, you're not going to get these problems wrong. Speaking of getting problems wrong on the test, just another little blurb I want to talk to you guys about. Please, 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 on the test, give me the work you're doing, not just the final answer. You give me the final answer, I don't know if it's not exactly perfect. I don't know where you got it wrong, and I may have to take the entire points off. But if I see that it's just an arithmetic mistake, you're probably going to get huge amounts of partial credit. Please, on your tests, put all your work. 98% of you, well, 90% of you guys do that fine. 10% of you, you're doing like a, you're not doing it, okay? And I can't give you partial credit when something is wrong, okay? All right, off to the side. All right, those test statistics, we had 3 that we went through before. I'm going to write them on the board again, right? And then I'm going to introduce, just like we did the last time, the test statistic for proportions. And the test statistics for proportions looks different, okay? Just like in the confidence intervals, the 4th one was for proportions, and that one looked different as well. The formula looked different. So the exact same thing applies here. So let me turn this off, sharing, so that we can go and go back to share camera. You guys should be seeing me again, is that correct? All right, so, okay, yes, okay. So a couple different things, right? I'm going to write the test statistic, right? But notice in the charts, in the bottom chart that we had, which was the blue one, right? And we had a other one up on top. In the case of a two-tailed test, this was the acceptance region, and this was the shaded ones were the reject. This bottom one comes from the tables in the back of the book, right? And This plus this is the alpha. So if alpha equaled 98%, whoops, let's do that. Alpha equals 2%. That means 98% of the time you will be in the acceptance region, assuming that the null hypothesis is true. And 2% of the time you're going to be in the shaded area, which means this is 1% and that's 1%. Okay? Different alphas will have different amount of shades. Right? And so what you want to do down here is calculate, if you are using a z-table, you will calculate the cutoff value. This will be the minus z cutoff value. These will be the edges on the normal curve or the T curve that are in the back of the book. Okay? So we have Z cutoff values for T cutoff values. Okay? These are not the same thing as the test statistic. You do these in one of those first steps, right? After you draw this curve, you figure out what your alpha is. It tells you, how much is in the shaded areas. If it's a two-tail test, you split alpha into two, right? If it's one-tailed, it all goes on the other side, okay? On one side or the other. And 1 minus this alpha is what the non-shaded area was, right? And where do you get this? You get it from the Z-table in the back of the book or the T-table, depending on whether it's Z or T. Cheat, always go to the T-table, right? Because the bottom line on the T-table is essentially the Z number, right? So I say, theoretically, if you're a Z problem, go to the normal curve, a normal table. If it's a T problem, you're going to have to go to the T table and you're going to need to know the degrees of freedom, which are n minus 1, right? Okay, but both of those you can get off of the T table. So we've drawn this and we have gotten the Z cutoff values, right? Now, in this last step, we now calculate the test statistic. And the 3 that I had on the board yesterday were, not yesterday, but Friday. It's the first one, the second one. There's a bar, X bar. What's the difference? We replace sigma with our sample standard deviation. We use that when n is large. We say, oh, just go ahead, do that, and use the Z formula. Okay? The third one was okay. And we use this third one when our problems did not know what sigma was, so we used S. Because n is small, we don't think that our estimate of S is good enough to use the normal table, so we use the T table instead. So this was the case when n is greater than. So those were the 3 major formulas. Now, I am going to deal with proportions. In a proportion problem, we are looking for the percentage of an event happening, right? Okay. We might be interested in the percent of what's the right word here? The percent of people who are going to vote for for Governor Abbott when he gets reelected, right? If you're a Republican strategist, right, a positive vote is good, a negative vote for whoever is running against him is bad, right? And you want to be looking at the probability he's going to win, right? And so one of the things you're polling right now, and you got a little bit of bad news this weekend if you were on his campaign staff, okay? And you asked the question of people in general. If you were to vote right now, would you vote for the governor or would you vote for another individual? And the other individual was, who's the actor? McConaughey? Whatever. Okay. Anyways, you want to take that percent that's going to vote for your person. And if that percentage of the population is more than 50%, you feel pretty good. My guy's likely going to win this thing, right? If your percentage is under 50%, that means these guys are going to vote for the other guy. That's bad for you, right? So you will probably go out and having your political pollsters go out and take a sample and say, well, what's the public opinion about my guy? Up or down? Right? And you may want to test something along those lines. Okay. The governor may claim, don't worry about that stuff. 70% of the people out there love me. More than 70% of the people love me. Don't worry about the election. Right? You work for his political campaign. Are you going to listen to your governor who says, don't worry, 70% of the people love me? Or are you going to say, well, that's fine and dandy, but I hope you don't mind if we do a survey anyway to see if what you say is true, right? In which case you're doing a hypothesis testing. But what are you testing? To see if the percentage is what the governor says, or the percentage is greater than or equal to what the governor says, if that's what he's saying, right? The governor's saying, my approval is greater than 70%, then the null hypothesis is going to be that he's greater than 70%. Because do you want to tell him he's a liar if you're working for him? Probably not. Okay. If the governor really just said, oh, I don't want to influence your decision, he would have said, go out and do what? He would have said, I don't know what reality is. Go do a survey and come back and tell me what you get in terms of my approval rating. At which point, not knowing anything, you would have done what? You would have done a confidence interval. You would have gone out and gotten the percentage of people who said, yeah, I vote for the guy again, right? You know your sample's not right, so you're going to have to put padding on both sides, and you can go to your boss and say something along the lines of 99%, where I have 99% confident that your approval rating is between 40 and 43%. At which point, hopefully, the governor says, shit, I got to do something to get myself reelected. You're that sure it's between those two numbers? Yes. Well, is it possible I might win anyway? Yeah, it's theoretically possible. Are you guys going to Vegas to bet on me? Hell no, we're not going to bet on you, right? Is it theoretically possible you pull this off? Yeah, right? That's a confidence interval. When the guy says, I don't know, go find out and tell me what you find out, right? A hypothesis test, we're going to test his claim, right? So anyways, oftentimes these have to do with percentages, okay? Oftentimes problems like this have to do with quality control. We will be checking our widgets when they come off the assembly line. We know that there's a certain percentage that even in the best of days, you know, an air bubble goes in and destroys a piece of plastic. But what we want to potentially know is it different? Is today's production run different from what is normal? How do we measure it? By the percentage of products that are defective, right? We want to check the proportion that are defective and make some statement about that, right? So that formula is, I believe, in the next chapter, which would be chapter 10. Let me get to that. The test statistic. And this is for proportion problems. Okay. This one is P hat minus, and I'm going to, for a few seconds here, use the one that is in the book, right? And I told you on the previous chapter, I hate the way that it's done on the book, but let me do it the way it's on your book, and then I'm going to make my adjustments to it. Your book uses pi as being the true percent. Okay, so if you're doing a null hypothesis, pi would be the pi that is mentioned in the null hypothesis, the proportion that the person doing the null hypothesis claims to be the truth. Right? Okay. Now, just like your book uses pi, okay, as the true proportion in the confidence interval part, right? And I said I and a lot of other mathematicians and statisticians really cringe at using pi for that purpose, because in our world and in yours up until this day, pi equals what? 3.14 blah 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 blah, right? Okay. Pi has such a specific meaning that creating a new meaning for it here in statistics is a little problematic, right? So, but I'm going to put the formula down. The bottom of the formula is the square root of, okay, and all of a sudden that marker is dead. Square root of okay. So our z-test formula number 4 looks like this. Okay. As I mentioned, okay, I do not like the book's term of pi. Right? I will use p bar to still be the proportion that we got from the word problem, right? From the sample. P bar comes from the sample. I'm going to replace pi with p0, which would be the proportion that the null hypothesis says it is, right? Which means this thing is p0. Okay, and this is 1 minus p0. Okay. Here, p0 equals the null hypothesis proportion. The math is the same, except that my formula replaces that pi that has such an ingrained meaning in all Americans and actually around the world, right? Okay. Even the Russians use the same pi. They don't have apple pie like we do. Okay. P 1 minus P0. Right? So this formula, P bar up on top minus the proportion from the null hypothesis divided by square root of this thing gives us our z test statistic for proportion compounds. And that is the fourth of the equations, the test statistic equations, right? Up until now, we could have drawn all of the diagrams the identical way. One little exception. In proportion problems, this formula down here does not use a sigma or an S. It turns out we don't need either one of them. Okay? So, if you're doing a proportion problem and you are running back and trying to read and read and read and read and read, you know, what sigma is or what S is, and you can't find it, the reason is you don't need it. Okay? In proportion problems, you don't need it. When we did the confidence intervals, remember that fourth formula didn't need a sigma or didn't need an S. Same thing is true here. When you deal with proportion problems, you don't need them. Right? Right. Theoretically, you can calculate what sigma is using p zeros and 1 minus p zeros, which is essentially where this formula came from. So if you want to derive it, you can, but don't expect that you need to know it from the equation. Right? So this is the fourth equation. Now, I kind of mentioned I like this formula better than the one in your book. Okay? I don't want you to go get other books during your lifetime. At least go back to this book. I would go, if you have your book here, I would just make a notation on it here. You know, we learned this with P0, P0, P0. So 5 years, 7 years from now, when you pull out your stats book, okay, because you actually have to do one of these things, and yes, it will happen, okay, that you pull one out and it's got the P zeros in it, and so you don't get too confused with the pi, right? Now, if for some reason you take a different stats textbook and you open it up, there is a possibility that this fourth equation, instead of 1 minus P0, will have Q0. When you read the textbook, it says Q0 is the null hypothesis of not having a success. It's 1 minus Q0. All right. You go get a different textbook, all of a sudden you see this P0. I remember what P0 is. What the hell is Q0? Q0 is 1 minus P0. The probability. P0 is the probability of success. Q0 is the probability of failure. Probability of failure is 1 minus that. Okay, so this gives us our fourth equation. Okay, what I am going to do is, I've run out of time, I am going to put a set of homework problems out there, right? And I'd like you to go try those, figure out which one of these four statistics are the ones you got to calculate. Set up everything prior to that, figure out, is it a one-tailed, two-tailed, it's one-tailed, which side, right? And then draw the charts, figure out where the cutoff values are. And that will depend upon, you know, whether sigma is known or not. This last one is, if it's a proportion type problem, it's going to be a z, right? It's going to be that last formula. And then figure out what the test statistic is, go back, figure out, is this in the acceptance or rejection region? And write the answer down, right? I'm going to put this up, and then on Friday, I am probably going to give you the answers, right? So that you can study off of the answers. Try to do the homework before Friday, right? So that if you've got any problems, you can talk to me, and we will do some more of these problems on Wednesday, and we'll actually do some problems on Wednesday, and then talk a little bit about the next chapter, which is when you are trying to compare two means, right? Again, the same thing we did in confidence intervals, we are now going to be doing with hypothesis testing. Do the two machines have the same results? Okay. When we look at third grade students at the end of the third grade and third grade students before they enter the third grade, did the professor or did the add one more year worth of reading level to their quiver, the student's quiver? Those are the things that we're going to focus in on. All right, with that, we will see everybody on Wednesday. Okay, and reminder message that we will have a test on everything confidence intervals starting today. I see there's two notes here. Yes, that probably had to do with if you could see the chart. Okay, thank you very much, and have a wonderful Monday. We'll see you on Wednesday. Bye-bye.